Chapter 14. Dual Nature of Radiation and Matter. Exercises pages 322 to 323. Exercises Q1.1, page 322. Choose the correct option. A photocell is used to automatically switch on the street lights in the evening when the sunlight is low in intensity. Thus it has to work with visible light. The material of the cathode of the photocell is 1. Zinc 2. Aluminum 3. Nickel 4. Potassium. Solution. Potassium. Exercises Q1.2, page 322. Choose the correct option. Polychromatic containing many different frequencies, radiation is used in an experiment on the photoelectric effect. The stopping potential 1 will depend on the average wavelength. 2 will depend on the longest wavelength. 3 will depend on the shortest wavelength. 4 does not depend on the wavelength. Solution. Will depend on the shortest wavelength. Exercises Q1.3, page 322. Choose the correct option. An electron, a proton, an alpha particle, and a hydrogen atom are moving with the same kinetic energy. The associated de Broglie wavelength will be longest for 1. Electron 2. Proton 3. Alpha particle 4. Hydrogen atom. Solution. Electron. Exercises Q1.4, page 322. Choose the correct option. If n red and n blue are the numbers of photons emitted by the respective sources of equal power and equal dimensions in unit time, then 1. N red less than n blue. 2. N red equals n blue. 3. N red greater than n blue. 4. N red approximately equals n blue. Solution. N red greater than n blue. Exercises Q1.5, page 322. Choose the correct option. The equation E equals Pc is valid 1. For all subatomic particles. 2. Is valid for an electron but not for a photon. 3. Is valid for a photon but not for an electron. 4. Is valid for both an electron and a photon. Solution. Is valid for a photon but not for an electron. Exercises Q2.1, page 322. Answer in brief. What is the photoelectric effect? Solution. The phenomenon of emission of electrons from a metal surface when electromagnetic radiation of appropriate frequency is incident on it is known as photoelectric effect. Exercises Q2.2, page 322. Answer in brief. Can microwaves be used in the experiment on photoelectric effect? Solution. No. Explanation. The photoelectric effect is totally a quantum physics phenomenon. A single photon of light delivers a tiny bundle of energy to the metal and ejects a single electron with a very precise energy balance. Electric sparks emitted from metal points edges in a microwave oven are a macroscopic phenomenon that has no need for a quantum explanation. The microwave generator pumps hundreds of watts of electromagnetic energy into the oven cavity. The microwaves have a frequency of 2.4 GHz, which gives them a wavelength of about 12 centimeters. About 4¾ inches for those in the US. These intense electric fields induce currents to flow in the metal. Sharp points edges concentrate the buildup of the electrons, which can locally increase the voltage enough to cause the arcing. Exercises Q2.3, page 322. Answer in brief. Is it always possible to see the photoelectric effect with a red light? Solution. No, it is not possible, but due to present technology it may be possible. Explanation. The photons in red light do not have the necessary energy required to rip an electron out of its orbital. This needed energy is equal to the electron's work function. Because light behaves like particles rather than a continuous stream, even very high-intensity red light will never be able to overcome an electron's work function in this situation, as every individual photon fails to do so. This shows the particle behavior of light. Because of light behaved like a wave, the red light would be able to overcome the electron's work function with high intensity or a long time. Exercises Q2.4, page 322. Using the values of work function given in the following table, Tell which metal will require the highest frequency of incident radiation to generate photocurrent. Typical values of work function for some common metals. Metal. Work function in EV. Potassium. 2.3. Sodium. 2.4. Calcium. 2.9. Zinc. 3.6. Silver. 4.3. Aluminium. 4.3. Tungsten. 4.5. Copper. 4.7. Nickel. 5.0. Gold. 5.1. Solution. Gold is the highest frequency of incident radiation to generate photocurrent. Exercises Q2.5, page 322. What do you understand by the term wave-particle duality? Where does it apply? Solution. Depending upon experimental conditions or the structure of matter, electromagnetic radiation and material particles exhibit wave nature or particle nature. This is known as wave-particle duality. It applies to all phenomena. The wave nature and particle nature are liked by the de Broglie relation lambda equals hp, where lambda is the wavelength of matter waves, also called de Broglie waves ISCHR 6-Dinger waves. P is the magnitude of the momentum of a particle or quantum of radiation, and h is the universal constant called Planck's constant. Exercises Q3, page 322. Explain the inverse linear dependence of stopping potential on the incident wavelength in a photoelectric effect experiment. Solution. Exercises Q4, page 322. It is observed in an experiment on the photoelectric effect that an increase in the intensity of the incident radiation does not change the maximum kinetic energy of the electrons. Where does the extra energy of the incident radiation go? Is it lost? State your answer with explanatory reasoning. Solution. When electromagnetic radiation with a frequency greater than the threshold frequency is incident on a metal surface, there is an emission of electrons. It is observed that not every incident photon is effective in liberating an electron. In fact, the number of electrons emitted per second is far less than the number of photons incident per second. The photons that are not effective in the liberation of electrons are reflected, are scattered, or absorbed, resulting in rising in the temperature of the metal surface. The maximum kinetic energy of a photoelectron depends on the frequency of the incident radiation and the threshold frequency for the metal. It has nothing to do with the intensity of the incident radiation. The increase in intensity results in an increase in the number of electrons emitted per second. Exercises Q5, page 322. Explain what you understand by the de Broglie wavelength of an electron. Will an electron at rest have an associated de Broglie wavelength? Justify your answer. Solution. Under certain conditions, an electron exhibits wave nature. Waves associated with a moving electron are called matter waves or de Broglie waves or Scher 6-Dinger waves. The de Broglie wavelength of these matter waves is given by equals h_ip, where h is Planck's constant, and p is the magnitude of the momentum of the electron. If an electron is at rest, its momentum would be zero, and hence the corresponding de Broglie wavelength would be the infinite, indicating the absence of a matter wave. However, according to quantum mechanics, wave mechanics, this is not possible. Exercises Q6, page 322. State the importance of Davison and Germer experiment. Solution. The Davison and Germer experiment are probably one of the most important experiments ever, since it verified that de Broglie's matter wave hypothesis applied to matter electrons as well as light. From this emerged modern quantum theory, the most stupendous revolution in physics of all time. Exercises Q7, page 322. What will be the energy of each photon in monochromatic light of frequency 5 × 1014 Hz? Solution. Exercises Q8, page 323. Observations from an experiment on the photoelectric effect for the stopping potential by varying the incident frequency were plotted. The slope of the linear curve was found to be approximately 4.1 × 10⁻15 bs. Given that exercises the charge of an electron is 1.6 × 10⁻19 c, find the value of the Planck's constant h. Solution. Exercises Q9, page 323. The threshold wavelength of tungsten is 2.76 x 10 to 5 cm. A. Explain why no photoelectrons are emitted when the wavelength is more than 2.76 x 10 to 5 cm. B. What will be the maximum kinetic energy of electrons ejected in each of the following cases? I. If ultraviolet radiation of wavelength lambda equals 1.80 times 10 to 5 cm and E. Radiation of frequency 4 by 1015 Hz is made incident on the tungsten surface. Solution. Data. Lambda 0 equals 2.76 x 10 to 5 cm equals 2.76 x 10 to 7 m. Lambda equals 1.80 times 10 to 5 cm equals 1.80 times 10 to 7 m. V equals 4 times 1015 Hz. H equals 6.63 times 10 to 34 Js. C equals 3 times 108 meters per second. A. For lambda greater than lambda 0, V less than version 0, threshold frequency. Therefore HV less than HV0. Hence, no photoelectrons are emitted. B. Maximum kinetic energy of electrons ejected. Exercises Q10, page 323. Photocurrent recorded in the microammeter in an experimental setup of the photoelectric effect vanishes when the retarding potential is more than 0.8 V if the wavelength of incident radiation is 4950 A. If the source of incident radiation is changed, the stopping potential turns out to be 1.2 V. Find the work function of the cathode material and the wavelength of the second source. Solution. Exercises Q11, page 323. Radiation of wavelength 4500 A is incident on a metal having work function 2.0 electron volts. Due to the presence of a magnetic field B, the most energetic photoelectrons emitted in a direction perpendicular to the field move along a circular path of radius 20 cm. What is the value of the magnetic field B? Solution. Exercises Q12, page 323. Given the following data for incident wavelength and the stopping potential obtained from an experiment on the photoelectric effect, estimate the value of Planck's constant and the work function of the cathode material. What is the threshold frequency and corresponding wavelength? What is the most likely metal used for emitter? Incident wavelength, in A. 2536. 3650. Stopping potential, in B. 1.95. 0.5. Solution. Exercises Q13.1, page 323. Calculate the wavelength associated with an electron, its momentum and speed when it is accelerated through a potential of 54 V. Solution. Data. V equals 54 V, M equals 9.1 x 10 to 31 kg, E equals 1.6 x 10 to 19 C, H equals 6.63 x 10 to 34 Js, K equals 150 electron volts. We assume that the electron is initially at rest. Exercises Q13.2, page 323. Calculate the wavelength associated with an electron, its momentum and speed when it is moving with the kinetic energy of 150 electron volts. Solution. Exercises Q14, page 323. The de Broglie wavelengths associated with an electron and a proton are the same. What will be the ratio of I, their momenta, E, their kinetic energies? Solution. Exercises Q15, page 323. Two particles have the same de Broglie wavelength and one is moving 4 times as fast as the other. If the slower particle is an alpha particle, what are the possibilities for the other particle? Solution. As particle 2 is the X particle, particle 1, having the mass 1/4 times that of the A particle, may be a proton or neutron. Exercises Q16, page 323. What is the speed of a proton having de Broglie wavelength of 0.08 A? Solution. Exercises Q17, page 323. In nuclear reactors, neutrons travel with energies of 5 times 10 to 21 J. Find their speed and wavelength. Solution. Exercises Q18, page 323. Find the ratio of the de Broglie wavelengths of an electron and a proton when both are moving with the a same speed, b the same kinetic energy, and c the same momentum. State which of the two will have a longer wavelength in each case. Solution.